All right, wonderful. Thank you very much for the introduction, and thank you very much to the organizers for having me. It's really a great pleasure to be at this workshop. So my goal in this talk is first and foremost to tell you about an application that my collaborators have recently been developing in biophysics, and more specifically in super-resolution microscopy. Optimal transport has recently played a very important role in some of these applications, and I want to tell you a little bit about why it's been such a useful tool. And then I'm slowly going to tell you why this leads to the question of estimating optimal transport maps, and more specifically discrete ones, optimal transport matchings, under the setting of a Poisson deconvolution problem. So I'll try to motivate this, and then slowly I'll try to get to some theory about what are the fundamental limits of trying to estimate such mappings under deconvolution. And along the way, there will be interactions between kind of the existing body of work on statistical estimation of optimal transport maps and kind of existing work on Poisson deconvolution and mixture models and things of this type. So I want to emphasize that this is joint work with three wonderful collaborators. Shayan Hundrieser is a postdoc at the University of Twente, and I want to emphasize that he made many key observations in this work, and he jointly led this with me. Danila Litskevich is a former master's student at the University of Göttingen, and Axel Munk is faculty at the University of Göttingen. Okay, so let me jump in. The starting point for this talk, again, I want to start very slowly and to tell you a little bit about this application to super-resolution microscopy. And the starting point is this paper from a couple of years ago by Axel and by the groups of Axel and Stefan Jacobs at the University of Göttingen. And what they were interested in was to use optimal transport for a problem known as colocalization in biophysics. And I'll try to explain what this is through a couple of pictures. So what I'm showing you over here are microscopy images of proteins arising in a cell. Specifically, they were interested in the study of mitochondria in this particular application. So mitochondria consists of two membranes, and various points of these membranes, they come very close together. And the relevant scientific question of interest that they were trying to ask was whether proteins of these two membranes were involved in any relevant biological pathways with one another. And kind of a first order way to understand if two sets of proteins are interacting is to understand if they're co-localized, whether there's any spatial proximity between them. And this leads to the question, this is the term called colocalization in biophysics. This is the question of how can we quantify how close two sets of proteins or other molecules are under observation. And so what I'm showing you over here are microscopy scans of these two different sets of proteins from these two different membranes. You should imagine that scientists have some way of embedding what are called photoswitchable fluorophores. These are, small molecules that attach to these different sets of proteins that fluoresce in different colors depending on the group that they lie in. So one membrane is going to shine in green, the other membrane is going to shine in purple. And what we can see from these pictures is that there's a great deal of spatial overlap between these different set of proteins. Just to be clear, you should imagine that a protein in these pictures is just a little point mass. And there's a great deal of blurring that's arising in the pictures. And this is because the microscope that's being used to take these pictures is diffraction limited. And so as a result of interference effects, there's some non-trivial blurring according to some point spread function of the underlying microscope. On the left over here, I'm showing a picture of these two images overlaid, and what you can see is that indeed there's a great deal of spatial colocalization of spatial proximity of these two different sets of proteins. And the relevant question that arises is, what's a good one-number summary of the colocalization of these two images? And this is a classical question that arises in this area. And the typical approach that's been used for many decades is simply to do maybe the most naive possible thing that you could imagine, which is just to use a correlative measure of colocalization. That is to say, we can think of these two pixel intensity patterns, we can just vectorize them, and we can simply take their sample correlation. Just a pixel by pixel basis correlation of these two images, and that should give us a first order idea of how colocalized they are. Now, the problem with this is that it really relies on the fact that we have this blurring as a result of the microscope. That's really what enhances the fact that these are colocalized. But the problem is that in the last decade or two, there have been recent advancements in microscopy technology, and this has been, this is old news now, but 10 years ago, there was a Nobel Prize that was given for the development of super-resolved fluorescence microscopes, which really go beyond the diffraction barrier that existed for many decades before that for microscopy technologies. And now this is the modern picture that one is seeing increasingly in labs. What I'm showing you over here are the same underlying signals as in the first row that we had before, but now taken with one of these very modern super-resolved microscopes. And what we're seeing now is that this point spread function that arises due to the diffraction of the microscope has been significant, or its bandwidth has been significantly decreased. And that now we're really seeing much less blurring. We can really almost make out individual point masses, these individual proteins in these underlying pictures. And so now you can see what the issue is with the traditional view. If the traditional view is to use correlative measures to measure colocalization of these images, clearly we're going to get a very different answer in the second row than we would have gotten in the first row. And this is despite the fact that the underlying signal is exactly the same in the two cases. But just because the point spread function, the amount of blurring that the microscope is causing, has gone down, we will get a very different answer in the second row. So this kind of shows a deficiency of using correlative measures in this world where you have these very high precision microscopes which really go beyond the diffraction barrier that existed before, and it raises the question of developing new methods for quantifying colocalization. And as you can imagine, given the theme of the workshop, the proposal was to use optimal transport to derive a new measure of colocalization. So specifically what they proposed to do was to view each of these pixel intensity patterns as densities over two-dimensional space, up to normalization. I can view each of these as just two-dimensional densities. And their proposal was to compute the optimal transport problem between these two intensity patterns, and to use some function of the optimal transport map as a measure of colocalization. There are different functionals that one could imagine using for this problem. Maybe the Wasserstein distance is a natural first idea that might come to mind as a one-number summary. I could just take the Wasserstein distance between these two densities. That would seem like a natural first choice. They wanted a slightly more refined functional, which is defined as follows. It's roughly and I made a mistake over here. This should be less than or equal to. This is the CDF of the magnitude of the displacements induced by the optimal transport map from P to Q. Okay, so this is some other functional that they imagined using. Roughly, what they're asking is that for any given threshold tau ranging from 0 up to maybe the diameter of the support of the distribution, they're asking, and again, this should be less than or equal to, they're asking how much of the mass of P is transported within this radius tau somehow. Okay, and so why did they propose to use optimal transport? The answer is very simple. It's because optimal transport is well defined even in the resolution limit. Unlike correlative methods, which, as the bandwidth of this blurring kernel goes down to 0, correlative measures would not make sense anymore in this picture. They would just go down to 0 correlation. Optimal transfer will continue to make sense even in the limit where you really are actually resolving the underlying point masses of these pictures. So again, this is the usual reason why, one of the many reasons why in statistics we like optimal transport, that it doesn't place absolute continuity requirements on the measures being compared. That's exactly what's being leveraged in this application. And not only that, but you could even imagine that in this resolution limit, when you are actually down at the level of point masses, the optimal transfer map is actually giving you a very interpretable quantity. It's telling you which proteins are being matched to which other ones. This actually has an interpretation that one could use in the scientific applications. This is a picture from their paper to show you what these optimal transport colocalization curves look like. So here in red, I'm showing you this functional as a function of tau. So tau is ranging on the x-axis. This is on the scale of nanometers. So these figures are on the scale of a couple hundred nanometers. And what you're seeing over here in the red curve is for the top row, when we have a lot of blurring for a traditional microscope. In blue, we're seeing it for these super resolved microscopes. And again, the point that they're trying to make is, yes, you see a bit of a difference. You should see a bit of a difference, because otherwise there would be no need to use super resolved microscopes. If we had a functional that were completely blind to the level of resolution of the two pictures, we wouldn't need this advanced technology. So there should be a difference between these curves, but it's relatively stable. Whereas if I took a correlative measure between these two pictures, it would change by like a magnitude of 2, by a factor of 2. Okay, so that's the proposal that they made. And now, like I mentioned, that where I'm headed in this talk is that I want to talk about the statistical recovery of optimal matchings. And so now, at this point, I haven't told you why this is a statistical problem yet. A priori, these are just images between which we're doing optimal transport. And the reason this becomes a statistical problem is that the kinds of microscopes that are being used in either of these two rows are photon limited. They're fluorescence-based microscopes. And what that means is that in a fluorescence microscope, unlike the traditional microscope that we would have used in school experiments, where you would have a source of light underneath that's shining through the sample, and you effectively have infinitely many photons in this case. In a fluorescence microscope, what you're doing is that you're taking molecules which fluoresce, you're adding them into the sample, and with some probability, under stimulation by an external source, they will emit a photon with some probability at each of these locations. And these photoswitchable fluorophores that are added in there, they have a limited lifetime. They will eventually die out. So there's really a limit on the number of photons you will observe from any given location in this picture. And since these photons are emitted on a random basis, you have to take that into account and to really view these as just instantiations of a point process over two-dimensional space. Okay? And so the question is, can we understand how well we can estimate not just the optimal transport colocalization curve for these two given realizations, but if we actually want to understand what the population level optimal transport objects are, then we're led to the question of estimation under this kind of noise model. So that's kind of the basic background. And so now I want to start to slowly become a little bit more formal and to tell you what the basic kind of deconvolution model is that arises from this application. And then I'll slowly formalize the problem a little bit further after that. So let's start with the model that one observes in these microscopy experiments, ignoring the optimal transport aspect of this for a second and just thinking for one image, what is the noise model? Well, we can construct it in a couple of steps. The model that I'm going to be adopting is the following. I'm going to assume that we have some underlying space, let's say the unit cube in dimension d. I'm using dimension d just for the sake of generality, but really we're interested in the two-dimensional case in particular. I want to imagine that you have some underlying proteins, which are really point masses at locations theta I across the space. And I'm going to model the underlying signal, the underlying collection of proteins, by a uniform measure which is supported at each of these locations. I want to emphasize the uniformity of this measure. I really want a model where I'm treating the proteins as being equivalent in terms of size or any other characteristics for all intents and purposes, which is perfectly realistic in this application. For the level of resolution that we really have no way of distinguishing these proteins. We just want to view this as a uniform measure. So that's going to be the underlying kind of unknown signal of the problem. And what we should imagine is that when we're using any diffraction-limited microscope, or even a super-resolved microscope, there's an effective point spread function which causes a blur to the signal. So the first step is that we're not going to observe mu, but we're going to observe its convolution with some kernel. For simplicity in this presentation, I'm only going to imagine that K is the normal 0, the normal zero identity kernel. We study other compactly supported kernels in our work, but we'll just stick to the Gaussian case for today. I'm taking identity just for simplicity of exposition. Though, of course, in practice, you might imagine the case where the variance is shrinking, and that's an interesting question that we do not study. The next step is that there's going to be some binning applied to this density. Why is this? Is because, again, you could imagine this as I'm just representing the picture with some finite number of pixels. In practice, this is actually more important because these are scanning-based microscopes, which really take observations at a discrete set of locations on the underlying plane. So you really observe binned observations. And for here, BI is going to be a partition of the underlying space. I'm going to assume we're only observing not K-convolved mu, but really its integral over one of these bins. And finally, the stochasticity comes in the fact that you have this fluorescence, as I mentioned. Fluorescence is well modeled by a Poissonian distribution. And so finally, what we observe is not the histogram of the density, but really the histogram with Poisson noise added on top of it. T here is a parameter that indicates how much time the experiment was conducted for. Again, you should think of T as being limited due to the fact that these molecules that emit the fluorescence will eventually die out in the experiment. Yes?
Could you here also model the noise, which is really what you're doing already because you're convolving with K? You say, we have some theta I, we're adding Gaussian noise, but it's hidden, and then we're evaluating these K star mu Pi.
I don't understand the question. So yes, we have. So at this point, there's nothing stochastic yet.
But you could say, what we're observing is theta I plus Gaussian noise, and then counting how many there are in each Pi.
I think that would be an equivalent model, but you would need.
Because this is kind of what the.
You could think of it as a hierarchical model, where first I'm adding noise. I'm adding Gaussian noise to each of the individual theta i's. Then I'm binning, and then on each of these histogram bins, I'm adding Poissonian noise. That is probably an equivalent formulation of the model. Yeah. Okay, any other questions about the basic model? So I'm going to be using this notation for the rest of the talk. If anything is unclear, please let me know. And so again, of course, one doesn't observe all this stuff in the background. One only observes this final picture in an actual experiment. And this is why I say that those pictures I was showing you, you should really just view as a realization of this Poisson point process, this binned Poisson point process on the unit cube. Okay, so now let's come back to the colocalization problem and let's try to formalize it a little bit. The setting is going to be the following. I'm going to use script UK to denote the set of k-atomic uniform measures throughout the talk. And given two underlying signals, mu and nu, these are like these two, the green proteins and the purple proteins, if you will, in script UK, I assume that I'm given access to two images, which are modeled as two realizations of this Poisson point process, one with signal mu and one with signal nu. Yes?
So what exactly do we assume to know here? I mean, if let's say kappa or k is some arbitrary kernel, maybe a Gaussian or something, do you know it?
Let's fix it to be Gaussian for the talk.
So you know it?
You know it, absolutely.
It has a variance parameter, you know the parameter?
Yeah, and this is completely realistic. I mean, you know the apparatus that you're
sure,
using,
I
you know
just
its
want to understand
function.
about it. And the t is also known?
T is also known. You know, let's say you know how much time the experiment was run for. That's right. So you know everything over here except mu and nu.
Yes. So you assume that k is the same for both mu and nu?
That's right. I'm assuming, let's say, I've used the same microscope in both cases. So it led to the same convolution kernel.
No, I mean small k.
Small k. That's a very important question. This is where I'm going to put my theoretician's hat on and say I'm going to assume they're the same for the two, but that's a strong assumption. May not be realistic in practice. Now I'll say, in their more recent line of work, the way that they've been handling cases where you have different k is actually by going to unbalanced transport and thinking of cases where, some of these proteins may not match to other ones. If there are more proteins on one side than the other, some of them may not match to anything and things of this kind. So it becomes a more subtle story to do in the case where you have different choices of k if you want to do it in that way. So for today, I'm just going to assume we have the same number of proteins on either side, lowercase k. Good question. I'm also going to make the very strong, and this is truly unrealistic, assumption that k is known in advance. But let's just say for the sake of doing some theory and trying to understand. So the problem will already be interesting in this case. When k is known, equal across the two samples, how well can we do recovery in this model? Okay, and so under this model, there are two interpretations of the optimal transport colocalization proposal that they had. The original proposal that they had, the way I described it to you, is that the object of interest is this quantity over here. The optimal transport colocalization curve, not between mu and nu, but just between these intensity patterns. And that was kind of their starting point, is they wanted to say that somehow optimal transport should have some level of robustness to Gaussian convolution. This kind of reminds a lot of the Gaussian smooth optimal transport framework that Ziv has been developing over the years. This was their starting point, right? This was how I kind of described it earlier, is that there's a sense in which we expect this thing to be relatively stable with respect to the bandwidth of this k. And there's a sense in which we could just look at the intensity profiles of these two pictures. And this is what, in the lingo of this literature, this is what would be called just an intensity-based coefficient. We're not trying to resolve the underlying objects. There's another perspective on their metric, though, which is to say, maybe I want to directly do the deconvolution, and I want to actually compute the optimal transport curve between mu and nu themselves. And this, in the lingo of this literature, would be called an object-based coefficient, one where you're actually looking at the underlying objects of the picture. And again, this can be viewed of a limit of this one as the resolution goes to 0. This is going to be the object of my interest in this talk, and this is the kind of object that I want to ask from a theoretical point of view. What is the optimal rate of recovering this kind of object? So I won't specifically discuss optimal transport colocalization, but I'll study the maybe slightly more general object of optimal matchings, and that's where I want to go today. So I'm going to, maybe the main result I want to tell you about is I want to give you a theoretical framework and to give you the minimax rate of estimating optimal matchings between discrete measures mu and nu under this model. And in order to get there, I'm first going to ask the question of, if I don't have two samples, I just have a single sample under observation, what is actually just the optimal rate of recovering a single one of these signals mu given observations xi from this Poisson model under the Wasserstein distance. And it will turn out that once we have a good understanding of this first problem, the second problem will follow from some stability analysis for optimal matchings of the type that have arisen in the optimal transport literature over recent years. So those are the two main results that I want to tell you about today. Are there any questions about the basic setting? Okay, and I want to emphasize also that the model that I presented is slightly tailored to this application, but maybe taking a step back, there are many elements of this model which are quite general. The fact that we have Poissonian noise and binning, it leads to some interesting technical challenges, which we will discuss, but maybe a more fundamental model, which is also captured by our analysis, is simply the one where you directly observe samples from k-convolved nu and from k-convolved mu, and you ask how well can I recover the matching between mu and nu. So that's another example of a model that one can analyze using these techniques. And the uniformity of these underlying signals will play a very important role in this case. It'll lead to faster rates of convergence, and it's also the fundamental assumption that we need in order to make sense of actually matchings between discrete distributions. Okay. So let me go to this first part where, again, I'm just focusing on the single sample case. I want to say how well can we solve the inverse problem? How well can we go from these noisy observations to the underlying signal? And so let me give you some background. There's a great deal of literature across many different areas that has studied problems that are similar in spirit to this one. And so I'm not going to aim to give a comprehensive review of this background, but just maybe the one thread of literature which is closest in spirit to the results that I'll be telling you about today is the literature on finite mixture models. And so I briefly want to tell you some prototypical examples from that literature, which will be our starting point. So in a Gaussian mixture model, unlike the observations that we have in our model over here, xi, one observes observations z1 through zn drawn from the density k-convolved xi. I'm using xi instead of mu to distinguish the fact that in a typical Gaussian mixture, we do not place the uniformity constraint that I have placed. In a typical Gaussian mixture, xi is simply required to belong to the set of k atomic measures, not necessarily uniform. So pk is meant to denote any k discrete measure which doesn't necessarily have uniform weights. This is the typical model of a Gaussian mixture. There are a few distinctions. Again, the first one is the uniformity distinction versus the non-uniformity distinction, and this will play an important role. Another distinction is the fact that over here, we have a truncation of the underlying density in our observation space. And that presents very interesting technical challenges, actually, in the sense that the underlying observation space, the unit cube, it's not all of RD. It's just a subset of the support of the Gaussian density, whereas over here, we really have observations from the entire non-truncated density. So that's one other distinction between these models. And then, of course, there's the binning, which will play less of a role in this particular talk. So there are a few nuances between these models. But nevertheless, it's very useful to have this background on Gaussian mixtures. And here's an example of a prototypical result that exists in that literature. This goes back to a paper by Heinrich and Kahn from about 7 years ago. And they were the first to establish the sharp minimax rate of estimation in a Gaussian mixture under the Wasserstein distance. And they also did this for much more general classes of mixtures than Gaussians. And here's the result that they proved. They proved that for any k greater than 1, the minimax rate of estimating the underlying signal under this Gaussian mixture model under the Wasserstein distance scales at this rate. So maybe there are people from a lot of audiences, so maybe I'll just unpack what this minimax risk is trying to say. What we're saying here is we're saying take the worst case signal, the worst case mixing measure in the underlying parameter space pk. I want to ask for that worst case xi, what is the risk, what is the accuracy of estimating that xi? And now I want to ask what is the best estimator, the best estimator xi hat n, which is based on these IID samples z1 through zn. What is the best estimator which can control this worst case risk over the parameter space? And then what is the rate of convergence of this optimal estimator? And the rate of convergence that they found was n to the minus 1 over 4k minus 2. So let me try to interpret what that rate is saying. This rate, we can try to look at the two extremes of this rate. On the one hand, we can try to take k equals to 1. When k equals to 1, this is the rate n to the minus half. It's the traditional central limit theorem rate of convergence. And that shouldn't be surprising, because when k is equal to 1, this is just a sample from a Gaussian, from a single Gaussian with a mean theta 1. And so this is just Gaussian mean estimation when k is equal to 1, stands to reason that we should get n to the minus half as the rate of convergence. On the other extreme, when k is close to infinity, morally, this approaches a non-polynomially decreasing rate of convergence. And this matches the fact that for smooth deconvolution, when you're trying to recover an underlying signal which is not discrete but actually continuous, it's known that the minimax rate of estimation under the Wasserstein distance is some logarithmic rate of convergence. So the two extremes of this picture match, and this happens to be the rate in the middle of those two extremes. Okay, it's a generally exponentially It's a rate that generally depends exponentially on the number of components k. And so Heinrich and Kahn proved that the maximum, well, they studied some minimum distance estimators, but in particular, their analysis allows one to show that the maximum likelihood estimator is minimax optimal under this picture. This was followed up in some more generality by a recent paper from the group of Long Nguyen at Michigan. And in a separate literature, it was shown that moment-based estimators are also optimal for this kind of a problem. Yes, question?
Yeah, may I ask a question? The meaning of expectation in this form, the Wasserstein two distance is deterministic if you have the worst measure and the best estimator. Why do we take expectation?
I'm taking an expectation over the randomness of z1 through zn. So this psi hat n is a function of z1 through zn. So it's a measure. This is a measure valued function. It takes in z1 through zn and it outputs a measure in this underlying space. The expectation is taken over that randomness. Any other questions about this background result? Okay, so that's the picture for Gaussian mixtures. And so now let me tell you what the analogous picture is in our model. What we find is that, again, our model is the one where we observe xi's from this binned Poisson deconvolution model. And in this model, the sample size that we had on the earlier slide, which was called n, should be viewed as analogous to the time parameter t, which governs the amount of time that the experiment was run. It's natural to view these on the same scale. And what we find is that with respect to this time parameter, the minimax rate of estimating this underlying uniform signal mu is t to the minus 1 over 2k. So what are we seeing? Roughly, we're seeing that, again, we have the same qualitative picture, that when k is equal to 1, we get the parametric rate of convergence with respect to t. When k is going to infinity, we get something approaching a logarithmic rate of convergence. But in the middle, this is a generally faster rate. It's quadratically faster than what we had for Gaussian mixture models. And again, there are many nuances between these models, but really the fundamental one which causes this distinction is the uniformity assumption on the underlying measures. And it was actually known from past literature that in a two-component Gaussian mixture, it was known that the minimax rate for estimating a uniform mixing measure is faster than the one up over here. As far as I know, this had not been established for Gaussian mixtures with more than two components. And so this is the rate that one gets in this problem, but it's also the rate that one expects for that distinct problem. It's natural to expect that uniformity would improve the rate of convergence because it's effectively reducing the number of degrees of freedom of the model. In general, a general k atomic measure has 2k minus 1 unknown parameters. It has k underlying thetas. It has k minus 1 masses associated to each of these points. Whereas in a uniform, when you have an underlying uniform measure, you only have k degrees of freedom rather than 2k minus 1. So it's natural to expect that you'd get an improvement in the rate of convergence due to that fact. But it turns out that that doesn't explain the story fully. It turns out that if I gave you a Gaussian mixture, even a two-component Gaussian mixture, with known weights, but which are not equal to each other, so not a uniform distribution, but one which has the same number of degrees of freedom as a uniform mixing measure, it turns out that the minimax rate is still this one over here. So there's an important role that's played by uniformity over here. There's something about the symmetry of this model which causes this improvement in the rate of convergence. And if I have time at the end, I'll try to elaborate on that.
Tudor?
Yes?
Can you say anything about the least favorable prior in both these two examples?
That'll be on the next slide. And OK, we analyze maximum likelihood estimators for this problem, and we show that they're minimax optimal. So I'll come back to that as well. OK, so least favorable priors. So let's try to understand. So even though we see an improvement when you assume uniformity in this model, even though we see that the rate of convergence is quadratically faster, it remains exponentially dependent on this parameter k. And it suggests that in a realistic experiment, when you have a large number of proteins, recovery of this underlying signal should be essentially impossible. So does this tell the full story? And it turns out that it doesn't, because the choices of signals for which you get these really pessimistic, exponentially degrading rates of convergence are very pathological examples, which are not reflective of the generic case that one expects in practice. So here's an example of the least favorable mu for which the minimax rate on the previous slide is achieved, that kind of worst case of that uniform measure mu. It's something of this kind, where all of the parameters theta of the underlying measure are contracting towards a single point. And this should make sense, because somehow if I take the Gaussian convolution of this thing, I should imagine that this will have just one big mode in the middle, and it should be very hard to tell apart one theta from another. So this is kind of the most difficult regime of this problem. But this is not reflective of the kinds of experiments we expect in practice, right? In practice, the pictures I showed you earlier had some filaments, they had some clustering structure, things were a little bit more well separated than something like this. Stands to reason that we should hope for better rates of convergence in general. And this turns out to be the case, and it turns out that the clustering structure of the underlying set of atoms of mu is really what drives the rate of convergence of the problem. And this was already known in the literature on finite mixture models, and I'll elaborate on that now. So yeah.
Just a few sentences ago, you said that if they're all collapsing, it is difficult to separate each or identify each theta I. But the Wasserstein loss is not looking at identifying each theta I, right? Is in some sense.
That's right, but identifying them is the same as being able to estimate them in a sense. So I'm just saying when they're all together like this, it's harder to tease apart which one is which. It's harder to tease them apart. So from the estimation point of view, it is also more difficult to estimate them when you have this kind of a picture. Just morally, thinking about what the Gaussian convolution looks like over here, that Gaussian density, the mixture density, is just going to have a very big mode over here. In this kind of a picture, it'll have a mode over here and a mode over here, and it should somehow morally be easier to estimate these elements than the ones on the left-hand side. Okay, and so let's come up with a model for capturing this clustering structure. So I'm going to now present a minimax rate where we're going to constrain the elements of mu to be clustered in this way. And the way we're going to write down such a model is as following. We're going to assume that there exists a measure mu0 with k0 rather than k atoms. So k0 is going to be less than k. And I'm going to assume that mu is in a neighborhood of mu0. So in this picture over here, k0 is going to be equal to 3. This is going to be, I'm going to imagine that there is some 3-component measure which has atoms over here, and that mu is in some small neighborhood of that one. In this picture over here, the best k0 I could have come up with is just equal to 1. I couldn't have come up with a larger k0, such that the atoms of mu0 are well separated, and such that that mu is in a ball around mu0. And so now I'm going to try to give you a minimax rate, not over the whole space of uniform measures, but over this ball. I'm going to say, how well can I estimate a mixing measure mu, which lies in a ball around such a mu0 with k0 components? And morally, the bigger k0 is, the faster my rate of convergence should be, because the more clustering, the more well separated the atoms must be.
All right, I just missed what mu0 is. Can you repeat that?
It's a modeling choice. It's not something that's inherent to the problem. It's a way in which I'm going to define a local parameter space. So I'm going to say, suppose you give me a mu0, which has k0 components, let's say 3 components. I'm going to ask, what is the optimal rate of estimating a mixing measure, which is in a ball around mu0 for some small epsilon? And this, it will turn out that, well, I'll show you the result on the next slide. We're just going to ask what is the minimax rate for estimating over these kinds of balls. And it turns out that we'll come up with estimators which are adaptive to mu0 in the sense that they will achieve, the rates of convergence that I will tell you will be achieved over this set by an estimator which does not need to know what mu0 is. It will achieve the rates adaptively without needing to know what mu0 is. But it will give us a more refined picture on what the rate of estimation is. So here's what that rate of estimation is going to be. What we show is that now if you constrain the parameter space in the way that I told you, suppose that you give me a measure mu0 which has k0 components, and then it turns out that there will exist an epsilon. Epsilon will be something on the order of the separation between the atoms of mu0, something of this kind. And what we show is that if you now take the supremum, not over all uniform measures, but over all uniform measures that are in a neighborhood of this mu0, the rate of convergence improves dramatically. Rather than t to the minus 1 over 2k, which I had before, I see a dependence now on k minus k0 plus 1, which means that the larger k0 is, the more clustering I have in the picture, the more this approaches the parametric rate of convergence. So clustering in the underlying picture improves the rates of convergence, and this again is the kind of the typical behavior that we expect in reality. So again, I want to emphasize that this kind of model, this kind of local minimax analysis has been carried out before. Again, the rates of convergence in past work are different than ours, but the idea of modeling the problem in this way is not new. This I've said already. When k0, or actually maybe this is worth emphasizing, in the special case where k0 is equal to k, when k0 is equal to k, that really means that all of the atoms of mu are well separated. In that case, we actually recover the parametric rate of convergence over here. On the other side of the picture, when there's a single cluster, you get the rate that we had earlier on in the talk. And the estimator is agnostic, so it's achieved adaptively by the MLE. So the same estimator that we had in the earlier slide is going to continue to achieve this upper bound. So this is just a kind of local way to understand its behavior. That's the role of mu0. It's not a parameter that arises in the estimator. Any questions about this? How much time do I have? 15 minutes. Okay, perfect. Okay, then I'll go over this briefly. I'm not going to belabor this, but I just want to emphasize, and this is now something that's much less well understood for mixture models. But
just
yeah.
one question. So you said it's achieved by the MLE. So this is in the in your Poisson setting, right?
In the Poisson setting, but also we can prove this in the Gaussian mixture setting as well.
Where the kernel bandwidth is now fixed, by the way.
Always, yes. It's been fixed from the outset, yeah.
You don't allow that to...
No, and then the problem would take on a very different flavor. If we had a location scale Gaussian type model, that would be a very different beast. Yeah, absolutely. Any other questions? Okay, so let me. Yeah, okay. I guess I'll go over this slide. So let me just tell you a further refinement that you can make of this picture. And this now is going to get to a deficiency of the Wasserstein distance for this problem. And this is going to be something that's not well understood for generic Gaussian mixtures, but it turns out that in our uniform regime, this is a refinement that can be carried out quite sharply. I'm not going to show you a formal result, but I'm just going to show you with a picture how one can refine these results further. So what we've shown so far is that the following rate of convergence is achieved focusing on this example, right? So if I have a true mu that consists of these black dots, I imagine I have some estimator, such as the maximum likelihood estimator, which will be these blue dots. And what we've shown in the first result, before looking at the local minimax analysis, what we showed is that the rate of convergence of the MLE is t to the minus 1 over 12. 12 because we have 6 atoms in this case. And then we refined this result by saying that actually in this picture, we have 3 clusters. And so the rate of convergence improved. The thing that it improved to was t to the minus 1 over 8. That turns out to be, that's the rate that we had on the previous slide when you have k equals 6 and k0 equals to 3. And these were convergence rates in the Wasserstein distance, which meant that the rate of convergence of these blue points towards the black points is t to the minus 1 over 8. It turns out that t to the minus 1 over 8 is actually not the sharp rate of convergence if you do this in an even more local minimax analysis. It turns out that the rate of convergence over here doesn't need to be the same as the rate of convergence here or over here. And this kind of stands to reason. It stands to reason that if I have fewer atoms in each of these pictures, somehow the deconvolution problem should separate nicely. That somehow I should be able to do the deconvolution problem very easily in this case, because I just have a single atom. And it should be much harder over here. But this is something that cannot be captured by the Wasserstein distance. The Wasserstein distance tells you that the entire measure in blue approaches the measure in black at some rate of convergence. It implies each of these rates within the subsets of the measures. It cannot give you a heterogeneous rate of convergence across this picture, but it turns out that you can obtain this. And so what we actually show, we derive a stronger loss function under which you can actually show the following heterogeneous rates of convergence, that here you actually get the parametric rate. This makes sense. This is somehow a faraway point. The fact that we have a lot of convolution down here shouldn't impact it somehow. And then you get a t to the minus quarter over here, t to the minus 1 over 6 over here. So the picture is much more heterogeneous than the Wasserstein distance would lead you to believe. Okay, I won't belabor this point, but just to say that one can make further refinements in this problem. Yes?
That's a good question. So in this case, why couldn't you show the Wasserstein distance gets t to the minus 1/6 somehow?
That's a good question, and it's plausible that we could show that. And so that's not captured. So in the local minimax framework that I had on the previous slide, t to the minus 1 over 8 was sharp. Maybe one can refine that further for the Wasserstein distance and show that you can get t to the minus 1 over 6, but you couldn't get something heterogeneous like this. And I want to emphasize again that the MLE achieves all of this adaptively. You never have to know anything for it to achieve these heterogeneous rates of convergence. Okay, so with all of that said, let me finally come back to the original optimal transfer problem that we started with, now that we know how well we can recover the underlying signal in each of these microscopy pictures, now you can ask, how well can I actually estimate the matching between those underlying signals? That's what I want to tell you about next. So again, recall the basic setup. We have two uniform measures, mu and nu, discrete measures, and we have access to two images, which I'm modeling as these, again, these two Poisson point processes, xi and yi, with underlying signals mu and nu. And my goal now is going to be to recover the optimal matching between mu and nu, where again, theta are the atoms of mu, eta are the atoms of nu. I'm assuming that lowercase k is the same for both of these measures, and so there exists actually an optimal map, an optimal matching between these underlying atoms, and I want to ask how well can I actually recover the coupling induced by this matching, which again was the object of interest in this optimal transport colocalization picture. Right, so roughly I'm going to put it pictorially, I want to come up with these blue errors essentially to approximate the black errors. And the way that we're going to measure errors under this model is going to be essentially to match the blue errors to the black errors. We'll do a second layer of optimal transport to measure errors, and we'll try to estimate the accuracy of this estimation problem under that kind of loss function. And one should think of this again as a discrete analog of a topic which has been discussed a lot in the recent statistical literature, the problem of estimating optimal transfer maps in the smooth setting. We heard about this in the earlier talk by Ricardo. And it turns out that some of the tools that have been developed in that literature will be able to bring them to bear for this problem as well. But before I get there, I have to tell you about one issue which arises, which is the fact that optimal matchings need not be unique. So I need to place some regularity assumptions on mu and nu in order to make this problem tractable. And so there are simple examples of this. Here's a classical one. Suppose I take mu to be the measure supported on these 2 points. Again, everything is uniform. Nu is the measure supported on those 2 points. It's clear that in this picture we have two optimal matchings. You can go in this way. You can map theta 1 to eta 1, but you could have also gone across the other diagonal to match mu to nu. So the matching is not unique, and so it doesn't make sense from an identifiability point of view to speak of estimation of this quantity in this model without placing further restrictions. So what's the restriction that we're going to place? It turns out that a sufficient condition to preclude this non-uniqueness of optimal matchings is a condition which, again, has been used a great deal in the smooth optimal transfer estimation literature. We're simply going to assume that there exists, we're going to assume that this optimal matching can be viewed as an evaluation of a smooth Brenier map over the underlying domain. That if our matching can be viewed as, have a continuous, nice vector field over the entire plane, if I can restrict that to these finite points theta I, and that map is equal to the matching, then that will be my assumption. I will assume that the matching can be written in that way. So what exactly is my assumption? I'm going to assume that there exists a smooth map over the unit cube. I want this map to be strongly convex. I want it to be strongly smooth as well. And I want this to push mu forward onto nu. So this is like some continuous Brenier map which pushes forward these discrete measures, one onto the other. And you can see in this picture that this condition is violated. It's violated because there is no strongly monotone vector field which can push a point in this direction and then push it in exactly the opposite direction in another part of the space. This violates strong monotonicity. You can find a monotonic vector field which will do this, but not a strongly monotone one. And so that's where this assumption will be violated. Okay, so that's the role of this assumption, and by having a parameter lambda, I'm quantitatively pushing myself away from these degenerate cases, and I'm going to ask what is the optimal rate of estimating matchings over the space of measures mu and nu for which there exists a map strongly monotone and strongly convex that satisfies these conditions. I'm going to denote, yeah.
Do you need both sides? You probably need only one side.
I need both sides, actually.
For your proof, but
for the proof.
For this?
No, for this, absolutely. If I wanted uniqueness of the matching from mu to nu and from nu to mu, then I would need this. You're absolutely right, that for the uniqueness of just one direction, you don't need both sides of this inequality. For our proof, we need both sides. Yeah, excellent question. Okay, and I'm going to denote by script t of lambda the space of measures mu and nu for which there exists a map of this kind that pushes mu forward onto nu. And what do we get under this example, under this assumption? We're going to get the following. So the way I'm going to formulate the problem of recovering a matching is by looking at the couplings that the matchings induce. I'm going to let pi of mu nu denote the optimal coupling between mu and nu, Again, I call it a coupling, but it really is supported on the graph of a map. And I'm going to measure the accuracy of estimating that coupling using the Wasserstein distance over the product space. So this is now a Wasserstein distance not over measures on the unit cube like earlier. This is now a Wasserstein distance over the set of couplings on the unit cube. And I'm going to try to measure the accuracy of estimating that underlying coupling between mu and u, which again is supported on the graph of a map, by some estimator pi hat of t. Again, what this loss function is essentially doing is what this picture is saying, right? I have some matching from mu to nu, black to red, and I'm coming up with an estimator that's approaching it. What this loss function is going to do, it's going to pair each of the blue and black arrows across this picture, and it's going to measure the distance between the endpoints and the source points and add them up. Roughly, that's what this thing is doing. And what we find is that you get the exact same rate of convergence as we did for estimating the underlying measure. So clearly, this is a harder problem than the measure of recovering the underlying signal. To recover the source or the endpoints of this picture should be a statistically harder task than to recover the matching. And so the interesting thing is that we see that we don't pay a slower rate of convergence. We really get the same rate as for signal recovery under the Wasserstein distance. This is for the worst case where I have no clustering assumptions. One has an analog of this result also in the clustering case, where here you would have a k minus k0 plus 1 or something of that kind. I'm not writing that version just for sake of simplicity. And an estimator which achieves this rate of convergence is going to be a plug-in estimator. It's one where you simply use the maximum likelihood estimator on each side to deconvolve the underlying measures and to take the plug-in estimator, the matching between those estimators of mu and u. Okay, and what's the underlying ingredient? This is not a hard thing to prove once one has access to an existing result in the literature that Siva Balakrishnan and I derived earlier this year, which says that one actually has a stability bound of the following kind. This holds for matchings, it holds for more general, absolutely continuous measures as well, that the Wasserstein loss that I have over here is actually controlled by the Wasserstein distance between the underlying marginals. And again, the key regularity condition that one needs for such a stability bound to hold is this strong smoothness and strong convexity of the underlying optimal transport map. So Siva's going to be giving a whole talk about this tomorrow, so I won't go into the stability bound in more detail. How much time do I have left? 5 minutes, perfect. So then in 5 minutes, just very briefly, I'm going to try to give you an idea of how one proves all this. So again, the question of optimal matchings, it kind of follows from the stability analysis together with the results from the beginning of the talk. So in this last part, I just want to, in 5 minutes, sketch to you how one proves the results from the earlier part of the talk. In particular, I'll just try to sketch out this first result, the simplest version of our results, where we got this rate t to the minus 1 over 2k for recovering a uniform measure under the Wasserstein distance. And I'll do this in dimension 1 for simplicity. So in order for me to tell you about this, my starting point is going to be, again, to think about what one does in the finite mixture model literature. What does one do in that literature? Well, or what did Heinrich and Kahn do in their original proof of the minimax rate of estimating a Gaussian mixture? They combined two ideas. The first idea is a simple one. It's a classical one. The first idea is that if you're trying to analyze the maximum likelihood estimator of psi, what we do know is that the maximum likelihood estimator will achieve a fast rate of convergence for estimating the density of the Gaussian mixture as opposed to the underlying signal psi. Why is this the case? Well, it's known that the rates of convergence for density estimation under the Hellinger distance are entirely driven by the complexity of the underlying class of densities as measured by their bracketing entropy. And it's known that the bracketing entropy for Gaussian mixture models is sufficiently well controlled, and one can obtain the parametric rate up to some log factors for estimating this underlying Gaussian mixture density without much work. So this is a standard fact. And now what would the hope be? The hope would be that if Gaussian mixtures formed a nice, well-behaved parametric family, the hope would be that the Hellinger distance would somehow be locally quadratic in the following sense. You would somehow expect that, I'm being informal in my notation here, I'm thinking of theta hat as the vector of atoms of mu. This is kind of what would happen in a traditional parametric family, that I would expect that the Hellinger square distance would be on the order of a quadratic form of the underlying parameters with here the Fisher information of the model. This is what would normally happen in a traditional model, but the whole problem with Gaussian mixture models is that this Fisher information matrix degenerates. And this degeneracy happens when the atoms of the underlying measure are approaching each other. And this is the whole reason why doing theory for Gaussian mixtures is challenging. It's because of this degeneracy of the Fisher information. And so what did Heinrich and Kahn do? Using a very subtle argument, they were able to sharply characterize the kind of in a sense, the order of degeneracy of this Fisher information. And what they proved was a bound of the following type. You should think of this as if I didn't have this exponent here, this would be a kind of a traditional parametric bound. It would be saying that the parameters are in the same order as the Hellinger distance. What they proved is that this is true, but if you have this exponentially degrading exponent with respect to k. And this is really where the rate of convergence of their problem comes from. Okay, and I won't tell you how they obtained this, but there's a different perspective on their proof which arose later on in the literature, which it makes it a little bit easier to see what's going on in the problem, and this is the approach that we take. What was noted later on in the literature, this was in a very nice paper by Natalie Das, Pengkun Yang, Yihong Wu, and Harry Zhao at Yale. What they showed is that if instead of looking at the space of underlying uniform measures, I instead parametrize them in terms of their moments, this Fisher information degeneracy would no longer happen. And that it turns out that there is actually a Lipschitz dependence between the Hellinger distance of Gaussian mixtures and now the moments of the underlying signals psi hatting psi. So if what is this object over here? I'm just measuring the difference between the moments of psi hatting psi, the jth moment, and I'm taking the sum of moments up to 2k minus 1. Turns out that 2k minus 1 is the right number of moments to look at. And it turns out that if I'm parametrizing the problem in terms of these moments, this does have a Lipschitz dependence with respect to the Hellinger distance. And so this gives you a different perspective on the proof of the MLE. One could imagine first using this identity and then trying to relate the moment distance to the Wasserstein distance. And this turns out to be a simpler thing to carry out. And so this is kind of the approach that we took. What we proved, and this will be roughly my last slide, what we proved is now going back to our model, we tried to carry out these steps. What we said is the following. In a first step, we said, okay, Das et al. Tells us that it's easier to parametrize the problem in terms of moments. So let's do that. We want to bound the Wasserstein distance of the MLE. I'm going to translate the problem first into moment space. And when I translate the problem into moment space for uniform measures, that's where I incur this exponent k, which is different than for normal Gaussian mixtures. It's k rather than 2k minus 1. And now once I'm in moment space, I know from Das et al. That the moment distance is on the same scale as the Hellinger distance between the Gaussian densities. If I were in a finite mixture model, this would already scale at the rate n to the minus half. When you're in this Poisson deconvolution model, you have to do a little bit more work. You have to take into account that you're not observing observations from these entire densities, but rather they're truncations. And so one has to work a little bit harder to control this Hellinger distance. What we show is that this can actually be controlled by now just the L2 distance over the observation space, which is the unit cube, and a few things of this type. So, and then one has to control this L2 object as well. But
so you lost the bidding with data processing inequality here for Hellinger?
I'm restricting this to the unit cube. Why would that follow from data processing? I'm taking a. So imagine. So in this problem,
aren't you quantizing these convolved measures?
Sorry?
Aren't you quantizing these convolved measures? I mean, that's the bidding, basically.
There's no binning at this stage. Ignore the binning for a second. Let's say the discretization went to infinity and that there was no binning. I'm telling you that the Hellinger distance is equivalent to the L2 distance, but now over the unit cube rather than over all of RD. So let's say you believe me that the Hellinger distance is equivalent to the L2 distance over the space of Gaussian mixtures, which it is. Then this would be equivalent to this with an L2 of RD. What we show is that Gaussian mixtures have this kind of strong property that it doesn't matter if you look at them over all of RD or just over a small subset of RD, that this is actually equivalent to the full L2 metric over all of RD. And this is somehow follows from the analyticity of Gaussian mixture densities. The idea that if I observed it over an open set, then I would know the entire density. That it's some argument of this type that's used to obtain this kind of equivalence, and this is one of the nuances that arises when you're working in this kind of a Poisson deconvolution model. Okay, so that's on a high level how one proves these things. I had a last slide to tell you that first inequality, but maybe it's fine for me to skip it. So I'm just going to go to the end and to say that maybe the higher level point in this talk, one of the higher level points in this talk has been that as sensing, imaging, or other metrology technologies improve, you're more and more faced with problems where you have an underlying discrete signal that you want to resolve. In contrast to traditional smooth deconvolution problems, where we're always plagued with logarithmic rates of convergence and things of this type, the discrete setting is one where a sharp local minimax analysis is possible. And it gives us a more accurate perspective of the underlying estimation problem. And like I say, as these kinds of technologies improve, you're more and more led to problems where the things that you're observing are underlying particles, underlying proteins, or things of this type. And in these kinds of problems, you can really get a sharp picture on deconvolution problems. So that's maybe one of the big themes of this talk. I tried to argue that there's an interplay between these ideas and ideas from the optimal map estimation literature, which has been mostly carried out for absolutely continuous measures in recent years. And finally, I emphasized the role of the robustness of the optimal transfer problem with respect to convolutional noise as a useful feature for imaging applications. That was kind of the starting point. Thank you very much.